Thank you very much. First, I would like to say that I'm very happy to be here. And I would like to thank you, the Chancellor and the President of the Academy for indicating me, and of course the Pope for accepting the indication. I am just a Brazilian physicist that lives in Brazil, South America, and I am a full professor at the University of São Paulo. And since I finished my PhD in the United States, I returned to Brazil with a determination to try to do science there as close as I used to do in North America. So I started my group. Today I have a group with more than 100 people. We have about 40 students. We are 4 faculties, and we call ourselves a group of optics that use optics in many things. And well, I have many scientific interests, all related with use of optics for something. My first interest, and maybe the main scientific activity, is in atomic physics, and then which is the field that I received my PhD from MIT in '87. And then I work with cold atoms. I have 2 members of this academy that are also very active in working with cold atoms. And the idea is to really remove the motion of the atoms to try to understand better. We're speaking about complexity. Even a single atom, like a hydrogen atom, is still for us a very complex. Sometimes we don't know how to write the problem. Sometimes we don't know how to solve the problem. So I think atoms, they follow in both categories that Bill was saying another day. And I've been passing through many different topics of research in cold atoms. Cold collisions, which is trying to understand how atoms get together, which is important, right? How they get together, how chemical bonds are formed, that kind of thing. I spent part of my life studying that. And in the last decade, I dedicate myself to the study of Bose-Einstein condensates. When you cool down too much, when you cool a little, it's nice to see the things in slow motion and get more details. But when you cool too much, the atoms change completely, and they start to behave themselves collectively as obeying the principles of quantum mechanics. And one of the manifestations is the superfluidity. Any fluid has viscosity, but in the case of bosons, which is one of the categories of atoms, when we cool down, they lose viscosity. And then a whole variety of phenomena start to happen there. And of course, we know at least 3 dozen of very good laboratories around the world studying different effects of Bose-Einstein condensate. And then I start to look for aspects that nobody else was looking, and I start to study turbulence in this superfluid. Turbulence, as you know, is a collection of eddies, that rotates in different directions with different angular velocities, and generate a situation that sometimes it is complex. But in the quantum world, turbulence is simpler than in the classical world. So that's a situation where studying in a more complicated system, which you say very cold, close to absolute zero, we can have a better understanding of turbulence. And this is what I'm doing for the last few years, try to understand, to get some physical insights on the phenomenon of quantum turbulence, which is turbulence in a quantum fluid, where the vortices are quantized and they react, and there are, at least that I count last time, more than 1,000 theoretical papers in quantum turbulence. And of course, there are more or less like 100 papers using liquid helium, which is another superfluid. But now we believe that in this system, which is smaller, finite, we can understand a little better. So this is one of the areas that I'm very interested in, and I'm progressing and trying to do my best contribution. But everything in atomic physics that we know is interaction of radiation with matter. And then about 15 years ago, I decided to start an applied part. How can I use everything I learned in this basic science to do some good things for my society? Then I start a laboratory in biophotonics, which is the use of light for detection and treatment of disease. And we did a very nice work that's now being applied in the clinics, which is how do you evaluate an organ that is going to be transplanted from the donor to the acceptor. And using fluorescence, optical fluorescence, we can now evaluate that kind of thing. And I learned very recently that United States are using the same technique now to evaluate a cornea transplantation. And my paper is there cited, so I'm very happy with that. But we go a little far from this. So my target is being cancer. How can we detect very fast cancer? And how can we treat very fast cancer? And to do that, we use a very old principle that's called photodynamic reaction. We try to introduce molecules in the tumor, excite by light, and produce a photoreaction that kills the cell immediately. And there are many groups around the world studying this, but we took more a physics point of view than a biological point of view. And we try to treat each tumor individually, and we're having a very good success. And the Brazilian government is financing 2 very huge projects for me. So I have 2 national programs, one for skin cancer, which is now, we have 100 centers spread in Latin America, including Brazil, Argentina, Colombia, Peru, Ecuador, Chile, in Concepcion. And now we start another program involving United States, the Johns Hopkins group, and Mexico for the treatment of cervical cancer. And we are having 100% elimination of cervical cancer with one application when they are in stage 1 and 2 and 3. More recently, I know people are very worried about environmental control, and I'm also. We patent a very nice technique that we believe can contribute for decontamination, which is trying to attract the mosquito of dengue and the one that transmits malaria to eat seeds. And then when they put the eggs and the larvae under sunlight, oxidize. And in the laboratory it's working very well, but we do not have yet the permission to do the external test. And we believe that that can be a good contribution for the control of dengue and malaria, which you know is a big problem in South America and in Africa too. Well, besides that, I'm very enthusiastic of science diffusion. In my laboratory, any PhD student has to produce at least one TV program explaining some basic science. And we have a TV channel that broadcasts 24 hours of science. And this has been very well received, and the government now wants to give me more money than I can afford. But we did now, with money of Brazilian government, special science kits, and we are putting in the public libraries, and instead of taking a book home, which I think is very important, the student takes a little part of a laboratory and do some experiment. We produce a collection of 20 of those kits involving physics, biology, chemistry, and astronomy, and and mathematics. And I was very happy to now learn that on the launch of the Olimpíada of Knowledge in Brazil, they're going to use our kits as one of the models. So, as a final statement, I always do science with a lot of passion. I don't get involved with a little bit of my soul. I get involved with everything. And I know very well that that's the way to do science, because other way doesn't work, And I know also that science needs to be done with reflection and a lot of concentration. But there is one new ingredient that I learned after I left MIT, that to do science, you need to have good relations, because you need to discuss, you need to receive criticism, and you need to improve yourself with that criticism. And I think I'm looking forward to have a good relation with this academy, because certainly this will improve the science I do, and I hope to contribute with the science that you all do. Thank you very much.